Hello, my name is Thomas Heiderscheit, and today I'm going to talk to you about near-field scanning optical microscopy, otherwise known as NSOM. This is you, and you are interested in looking at a variety of different things, whether it be bird watching in the mountains or looking at small things like cells. Now, normally with your naked eye, you wouldn't be able to fully see the bird or the cell, so you would use your tools. For instance, you would pull out a handy-dandy pair of binoculars in order to see the bird off in the distance, or you would pull out a microscope in order to see the tiny cell. Now, NSOM focuses on the limitations of microscopes. This limitation is known as the diffraction limit of light and was discovered in 1873 by Ernst Abbe, who proposed that when using wavelength lambda to resolve objects separated by delta x can be no less than lambda divided by 2 times the numerical aperture, which for visible light is typically roughly 200 nanometers. What this means is that if you have 2 objects separated by less than 200 nanometers, you will actually only observe 1 object. Overcoming this limitation would allow for the imaging of smaller objects than 200 nanometers. An idea for overcoming this diffraction limit was suggested by Edward Singe in 1928. Through using a screen with an aperture smaller than the wavelength of incident light, 2 regions were created. One would be where there is no diffraction limit, known as the near field, and a region where diffraction takes hold, which is called the far field. Focusing just on the near field, typically near field is described as a confined evanescent wave. What this means is as you move away from the screen, the near field decays exponentially. Typically, this has been found to be roughly 50 nanometers. Through placing your sample within the near field, you would be able to break the diffraction limit and image things smaller than 200 nanometers. This is the theory behind NSOM. Let's shift gears and start talking about instrumentation, starting with the probes. There are aperture and aperture-less probes, but I will focus primarily on apertured probes. So you create an apertured probe through pulling a fiber optic to a fine point and breaking it, forming a small hole. So as drawn over here, we have our probe that allows light to come in and form the near field. Now, in order to further increase the confinement that's needed for near field, we apply a metal coating to the outside of the probe. This tends to be either made of aluminum, gold, or silver. Now that we have a probe, let's focus on moving the probe in precise motion, otherwise known as the feedback. Now, I will specifically just be talking about the shear force. Now, how you have shear force feedback is through applying a tuning fork to your probe. Now, what this does is, as you move further or closer from your surface, you have different frequencies in that tuning fork. A simple analogy that shows the relationship between the tuning fork and the probe would be you are feeling sick at a party and need a friend to lead you to the bathroom. Unfortunately, the party is filled to the brim with people. Your friend, as the tuning fork, lets you know where to move when you get way too close to another person so you can easily get to the bathroom and throw up. Moving on to general instrumentation, you typically use a laser as your excitation light. You have your probe made out of a fiber optic with a small aperture. You place your sample very, very close to the tip with a tuning fork, which tells you the frequency as your tip moves further and closer. You then pair that tuning fork with a piezo stage in order to have very precise movement of your probe. So, using the laser light, you form the near field through your sample, which then you collect the light using a collecting lens, which typically you then send to an avalanche photodiode, which will turn light into electric signal, which then that signal can be sent to your computer in order to process and give you data. And with that, that is the basics of near-field scanning optical microscopy. I'd really like to thank you for listening and hope you learned a lot. Bye!